Okay, welcome to the second full-blown lecture on calibration. So far we've talked about the topic of calibration, we've introduced ideas of expected values, we've used that to derive an optimal curve fit for calibrations, and to produce an equation that models data. And now we're going to talk in a little more detail about more complicated cases. So we've done the easiest case there is, which is the linear case. Now let's show how this idea can be extended to start to fit more complicated calibrations. Let me talk just for a minute before we get started on some different cases where this actually is applied. So for example, in automotive sensors, for years there have been airflow sensors that are hot film or hot wires. These are little wires suspended in the flow of the intake, the air intake for the engine. And as air flows over the hot surface is cooled. Well, the surface is just heated electrically. It's just a chunk of metal with electricity going through it. Well, it's a little more than that. It's a metal whose resistive properties are very precisely known. So as I push electrical current through the wire, I can detect I can detect everything. I can know the voltage across the wire, I can know the current through the wire, which means if I'm a controller, if I'm a computer watching this, I can know what its electrical resistivity is. So I can know the heat I'm adding to the wire, and I can know its temperature. The faster the airflow goes over the wire, the better job the air does of wicking away heat from the wire. You can use this with nothing more than a chunk of metal in a tube to figure out what the airflow rate through there is. This is not a terribly precise method. It's not terribly accurate, but it works pretty well actually, and it's pretty robust, which is one of the reasons the automotive industry likes it. It's complicated though to calibrate it. It uses a very complicated calibration. Usually you need something like a fourth order polynomial to match these data. To calibrate these devices. So there are very physical, very real cases where a very simple sensor needs a very complicated calibration to make it work right. And it's worth it. The complexity in the math is worth it for the simplicity in the sensor. So that comes up all the time. Anyway, so that's just one example. We can come up with more. I'm assuming you believe me. All right, so let's set up the same sort of system, but let's imagine you've got a much more complicated. So this is what we've been seeing already. So imagine I've got some measured and some observed data, but imagine that now the sensor behavior is way more complicated. Like, we can put a line through that. We can do that, but it won't do a very good job. We could do a much better job if we used, for example, say a higher order polynomial. So again, there's a cost benefit between complexity of the calibration. Okay, you got to write a lot of code, versus accuracy, versus the how good is the how much error is incurred by using that very simple calibration versus a more detailed one. Okay, so for this, we need a more complicated function, right? So here, I'm going to write a polynomial to look like this. So let's use a cubic. Yeah, I'm almost out of paper. Okay, yeah, so there we go. So now instead of having only two coefficients, now we have four coefficients for a cubic. So you always have, for order n, you always have n plus 1 coefficients for a polynomial. Just in case you weren't aware, I'm sipping on my coffee every now and then. Just, it's one of the advantages of teaching from a desk. So if this is the case, the problem is still basically this. It looks more complicated, but it's still basically the same. We have a cloud of data in X and a cloud of data in Y. We need some sort of an analysis to figure out how this is going to go. All right, we're going to use exactly the same procedure we used last time. So let's walk through it step by step. So the first step is I need to define some, or I need some definition for error. So the error of each data point, again, we're going to define as the distance from my calibration. So this is my calibration. There's my calibration. So the error at any individual data point is equal to the distance between the measured data point, what is the measured data point, minus my calibration evaluated at the x. So basically, so what did I measure? What actual data point did I get? And how far is that from what my calibration tells me I should have gotten for that value of x, right? So whatever that difference is, that's my error. And we will minimize error in the system. So we will choose the A values, the A coefficients, that minimize the expected value of error squared in this system. All right, so in order to do that, let's start by actually writing the expected value for error squared. Okay. And I'm not, well, in other words, this is going to get pretty painful to write. I'm not going to bother to write all that out. Oop. There we go. So basically, yeah, you just take this whole equation and you got to jam it in there, and this keeps going. Okay, well, that looks awful. So remember what we did last time? In order to minimize this, we need to choose values for A0, or A0, A1, A2, A3. We need to choose values for these coefficients, where this error, if we were to visualize this error, if every single one of these is an Etch-a-Sketch knob where you're turning the knob and watching something move around, we need to choose values of these where the error reaches a minimum. That is, so it's a little change in each of these parameters doesn't really significantly affect the error anymore because you're at a flat spot. You're where the error is minimum. So in other words, the partial derivative of each of these of the expected value of error squared with each of these is equal to 0. So we can set up a system of 4 equations and 4 unknowns using this method. We're not going to solve it. It's going to be a matrix, right? But this is how computers do it. This is how the algorithm works behind the scenes to put a curve fit through things. So how does this work? All right, well, let's start by taking the partial derivative of the expected value of error with respect to just A0. This looks complicated, this looks daunting, this looks panic-inducing. No, it's actually not bad, because remember, when you take a partial derivative, you're going to assume everything else in the system is a constant, right? So basically, all these variables, everything else, the only thing that we're going to treat as a variable is A0. That's it. That's the only thing we're going to pretend is a variable. So here we go. So the partial derivative of this with respect to A0 is this. Keep the summation the same. I need to deal with the squared first. I don't touch anything inside. All right, and then I need to multiply by the inside derivative, which for a naught is just -1. Okay, not so bad. I'm going to do the same thing for a1. It's really going to be identical here. The inside doesn't change. There's a pattern we're going to benefit from. So we really don't have to do as much work here. Only this time we're differentiating with respect to a1. So here the inside derivative is -xk. All right. Again, we're going to do that exact same thing. The guts of these parentheses are not going to change. This time we're going to differentiate with respect to a2. So here we get a -xk squared. Same thing down here. Guts of the parentheses don't change. And now here we're going to get a -xk cubed, because we're differentiating with respect to a3. Okay, and that's all divided by n. Okay, so we've done it. We've taken the partial derivatives. Now we just need to rewrite them in terms of expected values. To do this, what we're going to do is distribute is the word I'm looking for, each of these terms through the parentheses and then split up the summation. All right, let me show you what I mean. So in other words, let's rewrite just the a naught equation. All right, so this is what we just got. So, yeah, this is just recopying what we had over here. All right, we'll come back to this. All right, so I need to distribute, and here's what I will get. I can blow away the 2 for free because there's a 0 here. I want to keep the n. I could blow away the n if I wanted to, but I want to keep it because it'll let us get expected values back. All right, so -yk. After I'm done goofing around with distributing summations, I can rewrite this as this. Or there. I'm able to do that because I can just factor out these a's. That's really no problem. And we're left with these expected values. So Well, there's a bit of a pattern developing here. All right, let's do this one more time, and then we're just going to be able to see it. We're going to be able to see the pattern for how this works. So that was looking at just the A0 equation from here. Now let's look at the A1 equation. Let's look at this one right here and see how that goes. So copying it without really doing, without doctoring it at all. We start with this. There we go. So that looks messy. Let's make it cleaner. You can factor out that you can cancel out the 2 just by dividing everything by 2, no problem. And when we distribute, this time here's what we're going to get. Negative There we go. Notice that if I compare this line with this line, every term, because of this term out here, because from the partial derivative was different, we promote the power of x in every single term. And so now here, what we're going to end up with is this. This looks a lot like the equation for m when we did this with a straight line, which is not a coincidence. Okay, so we have one equation, 2 equations. I'll bet you can see where this is going. If we repeat this process for the 2 remaining equations, that is the partial derivative of A2 and the partial derivative of A3, here's what we're going to get. It's going to follow the same pattern. Oh, whoops. Sorry. Really having trouble with my subscripts, apparently. There we go. Okay. And then not. All of the powers on x just get promoted by 1 every time. Good grief. I'm really struggling with my subscripts. My brain is on exponents, I guess. There we go. And there we go. We've got a system of equations. And so basically you've got yourself a matrix problem. So yeah, on the left-hand side, and remember, so this looks pretty daunting, but we've got 4 equations and 4 unknowns. The unknowns are the coefficients of the calibration that we want. The knowns, that is the things that we do know, are these data sets. We can easily calculate, as we've seen before, it's easy to calculate these statistics, these expected values on data sets. Right? So we can do that. We can calculate every single one of these. So basically, every single one of these expected values is just a number. It's just a number we pull straight from our data set. It can have a lot of decimal places, but who cares? It's it's going into a computer anyway. And when we're done, we just throw this into a matrix problem, and we can calculate our coefficients the A's. Now, I'm not going to solve a 4x4 by hand. No, dream on. I would throw this into the Python numerical package and invert it. Some of you can use MATLAB. That may be your preferred method for inverting matrices. Some of you have calculators that can do this, right? So yeah, there are lots of different ways to go about doing this. I would use Python for this. I wouldn't even hesitate. Yeah. So anyway, so that's what I wanted to talk about in this lecture is basically that we can do more complicated problems. We can get to more and more complicated curve fits. All right. Thanks for watching. I look forward to your questions.